All right, so what I'm going to do in this next 5 or 10 minutes segment is I want to start reviewing how to identify acid and bases in reactions. Now, we have a table, we have two tables, table K and table L, that tell us acid and bases, the generalities, but sometimes you get weak acid-base pairs. Now, we're going to learn about this, but the easiest and understandable definition of an acid is called the Arrhenius definition. The Arrhenius definition was very simple. To be an acid, okay, to be an acid, what you really do is have the ability to increase the H plus ions. So the earliest definition, okay, the earliest definition, and we'll do the acid and base guys tomorrow, but let me just wipe this out at the top here. The earliest definition, okay, was given to Arrhenius, and he said to be an acid, all you do is somehow increase the H plus ion concentration in water. Understandably so, that'd be an acid, because you know H pluses make the pH drop. We talked about that. And to be a base, Arrhenius said to be a base, all you have to do is produce hydroxides in solution. Again, understandably so. Our table of bases, excuse me guys, have hydroxides given off. Table of acids have H pluses. But we have found that there are compounds that produce acidic and basic solutions that do not follow this earliest and easy definition of Arrhenius. Okay, so if you hear the word Arrhenius, and you don't have to know many people, Arrhenius had the smallest limited scope of the definition of an acid and base. It's one that you intuitively know from my definition. So the red is the Arrhenius definition. Now, how do I know that this definition isn't all-encompassing? Well, if you go to let's stay here for a second. If we go to table K, you'll see CO2. CO2 is listed on table K as an acid, yet it has no H's to give off, H pluses to give off. So how does that work? Well, it must be from another definition. If you look at table L, where they list the common bases, you notice NH3 is listed there. Now, NH3 doesn't have a hydroxide, yet it's listed as a base. So there's another definition that will entail and encompass other chemicals that affect the pH balance of water. Let's talk about ammonia for a second. Now, ammonia, NH3, how does it make the pH increase if it's a base? Well, let's watch. Ammonia, if you learned, okay, is NH3. Now, what can it do? Well, in water, it has the ability to accept an H from water. Now, you may say, well, how does it do that? Remember, ammonia has 1, 2, 3, 4. We're back to bonding again. Imagine this, 5 valence electrons. Each H brings 1. And what's that number that nitrogen wants? What's that rule that we call it? It wants to have a stable 8 or octet. So it has a stable 8, which means it's got a lone pair. That lone pair attracts the H's from the water and can pull an H from the water. So this N with a lone pair yanks an H with the water, and the water becomes OH minus. And the ammonia molecule has one more, NH4 plus. So this, by able to yank H's from water to the lone pair, produced hydroxide ions, made the basicity go up, made the pH go up. So this acted as a base, not by giving off hydroxides, but by producing hydroxides by accepting an H+. So the next definition, called the Bronston-Lowry, we'll talk about this tomorrow, right definition, this guy is acting as a base, not by the Arrhenius definition, by something called the Bronston-Lowry definition. It's accepting an H+. Who's donating an H+? Who's giving off the H+ in the forward here? The water is giving off an H plus, so it's acting as the acid. NH3 is accepting, it's the base. Notice the double arrow. How do we go forward? Who's acting as the base in the reverse? Well, look. How does NH4 plus become NH3? How does it go from here to here? It gets rid of an H as it goes in the reverse. So this must be donating an H plus. When you donate an H plus, what are you called? An acid. And when you accept an H plus, you're called a what? So we have two definitions. The earliest, called Arrhenius, you produce H pluses to be an acid. The better one is the one when you donate H pluses. The earliest definition, you give up hydroxides. But we can see that this guy makes hydroxides because it accepts H's. All right? So, with that being said, let's go down and do the bottom one together for a second. Look at this reaction. Let's make it bigger. It's the last thing we're going to do before lab. We're going to use the current Bronson-Lowry method, donating, accepting. As I go forward, okay, this is the current state. This is the future. In the future, what happens to HNO2? It has one more or one less H. One less. How'd that happen? How did HNO2 become NO2 minus? It must have given off an H plus. So it acted as a what? Acid. Who accepted it? The water did. Now, in the reverse, H3O plus becomes what? H2O. It has one less. So where is the donation of the proton in the reverse? Who's giving it off? Does NO2 minus have any to give off? No, so it must be that the H3O plus is giving off an H plus. This is acting as the what? Acid, and this is accepting as the base. What you must be able to do is take a weak acid-base equilibrium. These will not be posted on table K and L, and decide who the acid and who the base is by looking at, hey, what does this become in the future? Oh, it becomes one less H. So it must have donated an H. It's the new definition. Donating an H plus is a better definition than Arrhenius because it encompasses more elements that are acids. And the water accepted an H. Okay? So my two bases are here. My two acids. We'll get to conjugate tomorrow. Okay, let's talk about today's lab. Turn that off now, thanks.